There, officially welcoming everybody to Garbage Day back in the basement, even though it's 60 degrees outside and 51. I'm assuming everyone can hear me and see me okay still? Good? All right, let me know if that changes. I have formative assessment number 2 up. I updated grades this morning. Your next task after this is homework. Homework 2 is out and due next Monday. I'm going to assume that we don't have questions about that yet. Is that a fair assumption? Okay. Your question might be, how could you possibly think I have questions about something that's not due for 6 days? And that would be fair, but I feel compelled to ask. So that's next up. Let's see. Then we have questions about time-varying predictors and model specification. So there was some variety, I would say, in how folks approach this. It looks like there's some confusion as to what person mean centering results in with respect to the level 1 predictor when it's paired with the level 2 mean versus without. So those are the questions number 1 and 2 here are focusing on that idea, and then 3 is focusing on between versus contextual. So I wanted to build us a little chart, and I probably did this in the clustered class, so this will look familiar to you, but it'll be different notation in terms of what you get and what it means with respect to main effects first, and then we'll try to talk about what happens in more complex models that also include interaction terms. So when I have one choice of options here, which I call variable centering, because the common idea is that you're centering using a variable and not a constant. So in the clustered class, it was the cluster mean of the level 1 predictor. In our longitudinal class, it's the person mean of the time varying predictor. In other contexts, it might be some other type of aggregate, but the fact that it's a variable is the important part. So if I'm creating a level 1 predictor, in the notation I had called it within person X. And how do I make that? If I'm using person mean centering, what would this look like? Like if you were writing code to do this. Feel free to talk, feel free to type. If you were writing code to do this, how do I
It would
create this variable?
be the main variable minus the mean for each person, which you would like create ahead of
Yep.
time.
Yep. So we have, if I go
Oh, I
with
like OG variable.
the what? I'm sorry? OG
Kendall
variable.
called it the OG variable.
You know what? I like that better. OGX minus person mean X. We'll leave off the constants for right now because that part doesn't really matter, but it would be the original person mean, not the centered version that's been rescaled. So yes, OGX for original. And then at level 2, if I have person mean X, then that would be just the person mean of OGX, like that. So trying to define at level 2 what this variable actually means. So in terms of, I'm going to actually add a column here. Not that big, just need a little one. In terms of the information that these variables contain, would you say that this one within person X has level 1, level 2, or both in terms of what then results for this within person variable? We got a bunch of fingers for 1. Yes, indeed here. So I'm going to abbreviate level 1 within. And this has to be centered because that's going to bother me every time I look at it otherwise. Yes, I am of that kind. You know this. You've met me. The level 2 variable then, the person mean. Now, does this have level 1 information, level 2, or both? Just 2. Okay, level 2 between. So then if I put this new within person X variable in my model all by itself, what effect am I going to get back? Your choices are within, between, contextual, or smushed. Are we making W's? Is that what this is? Excellent. Within, yeah. It has to be that way because that's the only thing that's left in the variable. You've segregated them ahead of time so that you can understand more readily what the slopes have to be reflecting when you put them in the model. And so at this point, if I leave out person mean x, what am I assuming about its effect in the model? What am I assuming its slope to be? Yeah, I like the finger questions. So I'm going to put that like that. See if Excel lights. That's it. Okay. So far, so good. Now, if I decide to put in only the level 2 predictor, I leave out within person x. What do I get back? Within, between, contextual, or smushed. That's a B for between. Is that actual sign language, or are we just making shit up at this point? Making shit up. Cool. Yeah, I don't know speak.
Making shit up.
Okay, I don't know
Always.
sign language. But that's right. What are we assuming about the level 1 slope for within person x if we exclude it? 0, exactly. And if we put both of these things in at once, what does the level 1 effect become? Yeah, it didn't have to change at all. Likewise, level 2 didn't change. So I like it this way. It makes life easier. You know what you get. Augix. I don't like that Excel overrides my capitalization. There we go. All right. In terms of weirdness, I would typically start with this one because when people think about putting predictors in the model, it's usually like the idea of a concept of a predictor. Like, I want to control for mood, I want to control for stress, I want to control for this. So putting it in at both levels at the same time makes a good deal of sense from an intuitive perspective. Now, if I have just this one, would this make sense to you? Would this be a reasonable approach? Like, let's say that you tried the within person effect and it wasn't significant, so you decided to take it out. Is that reasonable? I would say it's not unreasonable. You're saying that having more of this X predictor than other people on average matters, but having more of it than usual doesn't. That could be the case. So from a model specification perspective, I don't think that's unreasonable. I think that it might be interesting to your readers to know that more than usual doesn't matter. And to make that point explicitly, you might leave it in even if it is non-significant to say, hey, this is a between person thing, not a within person thing. That's information that I think would be relevant. How about this one? How about within only without the between part? Yeah, we're sort of making faces at this. This is technically not wrong, but it's a little weird. Because then what you're saying is that, well, more than usual is what matters, but it doesn't matter what usual is. Like, what it's relative to isn't even in the model. I find that a little weird. So for the same kind of reason, like if you end up with a pattern where something is happening at one level and not the other, I think that putting them both in so you can make that point, right? The idea that usual doesn't matter, but more than usual does, that's a salient point that having the model parameters to back up, I would want to make. Now, what about interaction terms? Let's say that we have something like within person X times group. Could I do that? Sure. And person mean X times group. So I would be saying that at level 1, the within person effect of more than usual depends on which group you're in. This is the type of story that your homework is using, by the way. At level 2, I would say that the between person effect of how much you usually have for X depends on what group you're in. Both of those things could be true. This one would be a level 2 interaction because person mean X is level 2 and so is group in this example. And this would be a cross-level interaction because we have within person X at level 1 interacting with group at level 2. Now, what if we had within person by between person? Could we do that? The effect of having more than usual depend on how much you usually have. That's what it would be. So if I thought about it from that perspective, and group is my moderator, and I replace that with person mean X, then I'm saying the effect of more than usual depends on how much you usually have. But I've only then allowed the within effect to be moderated by this usual amount. The corresponding version at level 2 would be that, and it would create a squared term. So that's where the age models get a little tricky, because this is what happens when you have like time interacting with age at baseline. So the squared term is merited from this sort of perspective. But let's go back to group for a minute, because that's a little bit easier to understand. So the within effect then, what source of variance is that going to explain? Level 1 or level 2? 1. Between effect, what source of variance is that going to explain? 2. Straightforward. When the residual variance at level 1 is explained, that may cause the random intercept variance to increase because of the way that it's computed, but the between person effect of the variable would then cause it to come back down. So you wouldn't see it necessarily if you put them both in at the same time. Okay, so I think that covers question 1. Any questions thus far? All right, constant centering. I'm going to save myself some typing here. Now, under constant centering, I am not subtracting a variable, right? I'm subtracting a constant. Does it matter what number it is? Nope, not at all. Not for what we're talking about here. It just changes what your intercept means, and it would change what the main effect slopes mean of any interacting predictors, but otherwise you can center it or leave it alone. Subtracting a constant does not change. So in the notation I had used in the slides,
So,
I call that
quick
TBX.
question for
Yeah, hit me.
for when you're centering it like that, would it need to be like something that's within the realm of your data? So like if you have data that doesn't go below 0, then like you couldn't. I mean, subtracting a negative is weird anyway, but you get the idea. Like it has to stay within the bounds of your data, probably.
Yeah,
It's like
technically,
a
yeah, if your
reasonable
data,
value.
yeah, if you have a negative, if the ranges of your data are negative, so like in years to death, in the example that we just did, that ranged from -16 to 0, then yeah, I had to add 7 to switch it so that the mean was like -7 as the midpoint. But I could have left it at 0, since 0 does mean something, but then I'd be predicting intercepts for dead people, and I find that just a little uncomfortable. So 0 rounded, of course. There wasn't any dead people giving us data, but there were a few folks that unfortunately died not long after, so it rounded to 0. But okay, so yes, what constant you would pick is determined entirely within the range of your data. The middle is usually a good guess. Sometimes the minimum can be helpful. So for instance, if you have like a scale score, centering it so that the intercept represents the minimum possible on the scale then makes it easier to talk about as x increases, right? Because that's the only way it can go, is up from there. I've seen people do that. If you have some representative value that folks would know what that means, so like 12 years of education is a high school degree in the US educational system, for instance, you might, like if you have a predictor for something like obesity and you have BMI, like the cutoff for obesity is like 30 or something, like so you could center that at 30 to say like this is a person who's on this cut point of this measure, something like that. But otherwise what the number is doesn't matter. So I'm changing the way that I'm creating this variable, still OGX to start with, but then subtracting some constant. At level 2, it's the exact same variable still. So we have the person mean of x. That means down here, when we talk about interactions for just a second, So in terms of the information contained in this variable, copy this down here so we can see it a little more readily. What is in time varying x? Within, between, or both? Is this a W or a 3?
Both.
Both.
If it's
Yeah.
on its own. Or,
Yep.
well, either, yeah.
Both. And how would I verify that? Like if someone handed me a data set and I have no idea what any of the columns mean, how could I figure out whether this variable has both? You know this. How do we figure out if any variable has between person versus within person? Yeah, intraclass correlation for it. Treat it as an outcome and predict it. If the intraclass correlation is 1, it's all between. If the interclass correlation is 0, it's all within. If it's somewhere in the middle, it's both. How about at level 2? Person mean x we said before was between. Have we changed our mind on that? Nope. It's the same variable. So we're just talking about the information they contain. Now let's talk about what happens when they go in the model. If I put in time varying x by itself, do I get within, between, contextual, or smushed? I think that was an S. I'll also accept this. That's the smushed effect. So I had several folks tell me in their answers that this within effect was also smushed at this point because the level 1 predictor was all by itself. That does not happen when you're using person mean centering because you have changed what is in the variable in the first place. If you don't change what is in the variable and you put in only one fixed slope for it, that is when smushing happens. And so to be more concrete, what are we saying about the between effect here? Are we saying that it's 0, like we did up here? No, we're saying something else. What are we saying? I don't know how to do gestures on this one. You can type though. You can talk. Same. Yeah, that's the problem. We're not saying that the between effect is 0. We're saying that it's the same as what the within effect is. That is what a conflated, smushed convergence effect says. Now, how about if I put in just person mean x all by itself? Well, it's the same variable. Yeah, so it works out to be the same thing as up here because it's just that variable all by itself. Now the both at once. The logic is when both of these variables are in the model at the same time, they compete against each other. They're correlated. TVX and person mean x are correlated. So each needs to have its unique effect controlling for the contribution of the other when they're both in the model at the same time. So if we have info rather than saying both, I'm going to make this a little more explicit. I have level 1 and level 2 in here. I've now controlled for the level 2 part. What do I get left? Yeah, level 1. So this switches to become the within effect, not because we set up the variables that way, but because the model is parceling, can't ever say that word correctly, controlling for the level 2 thing. So even though the variable that we started with contains different information, once we've controlled for the level 2 mean, that variable then becomes the within effect either way. Different variable, same result. What does this one become then? Within, between, contextual, or smushed? Yeah, C. This one is the contextual. Because it is also controlling for the level 2 part that is still within that time varying x. So contextual is bringing you up to what the full between effect would have been. So several of you wrote the relationship here. Between minus within equals contextual. Contextual. And within plus contextual equals between. So you can get back and forth. All right, questions or any that you want to hear again? So these are two different types of level 2 effects. One way to explain the difference is this: between minus within is contextual. What's another way to explain the difference between what these mean? What do we think?
It would be like it's the between effect after controlling for the within effect.
Yeah,
So
I like that. The easiest way that I can say it from that perspective is that contextual is controlling for what's happening at level 1, between is not. So my like absolute amount of grumpiness on this day, for instance, that's in the model. Contextual is what is the extra contribution a person mean grumpiness above and beyond just how grumpy I am today in an absolute sense. Like, am I a 5 today or am I a 7 today? A between effect does not control for the absolute amount of the predictor at level 1. It's just you're 2 units higher than usual or 2 units lower than usual, but we don't know what usual is. That hasn't been controlled. So I think that in longitudinal data, between effects usually make a lot more sense because occasions aren't entities that have their own characteristics the way that people are entities that do in clustered data. So in clustered data, within and contextual, I think is often more useful. In longitudinal data, within and between are. Let's see. Let's do variance explained. If I fit a smushed effect, is that going to predict the level 1 variance, the level 2 variance, or both? Yeah, this one's both. Because the part of it that has level 2 variance in it that we're giving an effect to in the model and saying it's equal to whatever the within is, that's going to predict random intercept variance. The within effect that is still within this is going to predict residual variance. So in practice, when you see a time varying predictor explain random intercept variance, that is a smushing problem. Level 1 cannot explain level 2. It doesn't work. What has happened is the level 2 part of the level 1 variable is what explained level 2. When I add the contextual effect, like if I start with within and add contextual, this should change the amount of random intercept variance explained to get it up to whatever the full between effect would have explained. So like in this model, we would see reduction within does level 1, between does level 2, and that's it. In this version of the model, the within would do level 1 and level 2, and then contextual would fill in the gap to get it up to whatever the full level 2 reduction should be. Okay, I think that's all I wanted to say about those things. How are we doing? We're feeling okay? Thumb check? Up. Now let's talk about interaction terms. If I put in time varying x by group, what kind of moderation am I saying when I just have it all by itself? Yep. It's a smushed cross-level interaction. By the same logic that the main effect is supposed to be carrying both the between effect and the within effect simultaneously, an interaction with time varying time varying x by group would say that group moderates the within effect to the same extent that it moderates the between effect. Same thing. So if you just have this by itself, then you have a smushed cross-level interaction. To unsmush it, you would have to have the person mean analog interact with group as well. So the same logic of not wanting to screw up your model applies to interaction terms. If you set it up with person mean centering, you're saying the within effect is moderated or the between effect is moderated, or they both could be, and that's fine. But here you do have to have both. Otherwise, you will have a smushed interaction for the level 1 part. All right. A couple of you had listed examples of smushing and model specification in your questions you wanted answers for folks who wrote that down. Did this help you, or are there still lingering questions you want to talk about? Assuming those folks are here. Because you know what? You can't answer questions from the YouTube. I'm not streaming this. It's not live. I'm not twitching. Is that a verb? Discording, twitching, streaming. Yeah. I actually used to stream, but then like my computer absolutely could not handle all of it happening at the same time. And I also wasn't going to check like the comments section on YouTube during class to respond to inquiries. Like, no, that's not happening. So I've got the chat window, and that's all I'm capable of. Okay, well, then I will let that go. I will put this up after class. You can take it with you for posterity if you wish. Let's see. We got that one and that one. Last one. In what kind of longitudinal designs do we need to worry about time-related convergence? Please give me an example. And I warned a couple people that I was going to call on them, and they're not here. So, but I warned the rest of you too that are here. So I know Hillary had a question about this, I think, with respect to the data you want to analyze, and Kendall did as well, perhaps, or you had an example. So what are your examples? Who's willing to share? Or the concerns you have that's related to this topic? Take your pick. The art of unbalanced time is related to this as well. So when do we need to worry about age convergence? Or smushing with respect to accelerated time? When do we need to worry about this?
When time is unbalanced and people don't all start the study at the same age.
Yes, when people start the study at different points along the time metric that you're using. So it could be age. In the case of, I think, Kendall, is it the HRS you were mentioning about this? The health and retirement study, as I recall. Yes, I know folks who did research using that data set. They grabbed a whole bunch of older people and measured them as long as they possibly could. Does that sound right? What you had written, essentially? So then we have people who vary in age cross sectionally at the first occasion, and then they follow them longitudinally. So it's the same exact set of concerns as for any time varying predictor. Time, or age, is a time varying predictor. So when it has both level 1 within longitudinal variance and level 2 cross sectional between variance, we got to worry about this. In academic settings, you might have kids that start out, say, third, fourth, fifth grade, and you follow them over time. Same thing would happen. You'd have to worry about whether this year's fifth graders look different than fifth graders looked 3 years ago, that kind of thing. Cohort effects. There's a couple others. I'm trying to think of the examples that I saw. Anyone else have examples? Or Hillary, did you want to talk about your unbalanced time questions? Because it's related to this. Unbalanced time does create this problem.
Yeah, I think I was just having a hard time identifying in my data, like whether it was balanced because everybody's measured 3 times. So that feels balanced, I guess. And they're on like roughly the same schedule, and that, you know, it's like, time zero, and then time two is like 4 to 5 years later, and then time three is like 10-ish years later. And so, and all of the students start at different ages. So they were in middle school when it starts, but you can obviously be like, sixth grade or fifth grade, whatever. I don't know how they divide this these days, but um, so my question was like, okay, when we're thinking about time being balanced or unbalanced, how specific do we need to get about it? Like the vagueness in the way that the authors were describing their resampling felt like, I don't think I would see this like in medicine or education or a different sort of field where these sorts of things are done really, really regularly. So yeah, and then thinking about, okay, so then do I need to pay attention to this and make sure that I'm modeling it appropriately within my data?
Okay, so let me make sure I'm following. We have kids who started at different ages within a range of grades, middle school ish. They're being followed. You said time two was 3 to 4 years later, and time three was 10-ish years later. Well, I think those kinds of observational designs, it would be very, very challenging to get everybody exactly 2 years later or exactly 10 years later, because you're like, when can they come back, right? Or when do they get around to filling out your survey, kind of thing. So it is unbalanced. The question is, what is the impact of that unbalance? And I think that is harder to anticipate, but it would depend on the context and it would depend on the range of how unbalanced it is. Like if you're talking 10 years later, these kids would be like 25 or something, and that's within, like 24.75 and 25.25 years of age, something like that. I don't think there's a big difference in 6 months, in 25-year-old people. I think there's a big difference in 6 months in like even my own kid. I see pictures of him 6 months ago and he looks smaller and different to me. So 6 months matters a lot sometimes and maybe not at all other times. I do think that you can set it up as an empirical question though. So you can predict each of your subsequent occasions, like predict time two, with how discrepant age is at time two. So, like if you get in your data and you figure out what the mean range is for the distance between time one and time two, use that to create a new variable where you are centering on that point. So then you can see whether time two outcomes look different in kids who are older when time two happened than they should have been, or kids that are younger. Like an offset, essentially, is what it would, you think of it that way. So you can answer the question like, oh, we tested it, didn't really matter how far time two actually was, so we're just going to ignore it. At least that's better than saying, it's fine, it's time two, don't ask any questions. That's what I would probably try to do, is find a way to examine it empirically. Other things you can do, I'm guessing that your data set probably has a mix of academic outcomes and like life outcomes and biology outcomes and stuff, since you're following kids over time and they're different ages to start with. So then you might have to think about, like, if you're taking change as a function of academic progress in school. I'll use my kid again. Like, he's turning 10 in a couple of weeks. He's in fourth grade. But there are kids in his class that are almost 11. There are kids in his class who are going to be 9 or stay 9, like if you skip a grade, right? So if you think of it that way, like just saying he's in fourth grade is an insufficient characterization of all the variation in time that's there. But if you put in age and grade, those things are going to be almost perfectly correlated across a wide range of ages and grades. So then in order to put in age, like you'd want to put in expected age at that grade level and then how far above or below you are, because then it's not confounded. And you can ask, like, if you're relatively old for the fourth grade, does that change your outcome versus being relatively young versus being right on schedule. Because kids are promoted ahead of time or held back for reasons, and those reasons may have something to do with whatever you're studying. So, long answer, your data are unbalanced. I don't know if you need to worry about it. You got to figure that out. That's my story. Empirical question. Not really trying to be glib, but you get my point. All right. Other questions on this topic? All right, let me get. All right, go ahead. Let me get my list of review topics. Make sure I'm not hitting anything.
So in the lecture that you gave last week about the death-based, like using that for time,
Yes,
um,
the death lecture. Uh huh.
I can't remember. Did you say that everyone in that sample had already, by the time they did the data analysis, had they already like, was everyone, was anyone else? People were, they all hadn't passed away at that point, right?
They some of them were still alive when the study stopped collecting data, but they were able to follow up with their official government records and find dates of death.
So then for like my research with the HRS data, since not every like there's still people in the study, obviously, um, then what would that look like trying to find another anchor point? This because like from what I'm thinking about is like even using dementia as like a point of concern around unhealthy aging. I'm watching a cat try to jump under the window. Um,
Cool.
like what would then be an alternate anchor point?
So I think if you're asking if you want to track change as a function of years to death, what do you do with the people who aren't dead? Essentially. Okay. Yeah, that is an argument, yet another argument why time is my preferred choice because you can include everybody if change is a function of time. In your case, what you would want to have, I think, is you can include when they died as a level 2 person moderator. And then you can have whether or not they're dead, and then like how long, like essentially how old they were when they died, relative, like how old they were like at when they died, and then whether or not they're dead. So something like that. And the same would be true of dementia. If you have an estimated date of diagnosis, then you can put that in as a level 2 moderator, like how long they've had these issues. But if someone doesn't have it, like you couldn't have change as a function of dementia progression in people who don't have it. So the same is true for any kind of intervention where people can elect to do it. So, for instance, I'm helping a student examine changes in science outcomes for schools who adopt a new curriculum. Well, the schools got to choose if they wanted to do this and when they wanted to do it. And I think there's probably reasons why schools chose not to or chose to and chose to do it first or last. And so if they were interested in looking at progression of science scores as a function of how long they've been in the program, we wouldn't know what to do with the schools who aren't in the program. But what we can do in that case is make a level 2 moderator. Did the school choose to be in the program and then when? And that can moderate their entire trajectory even before the program had started because they might have looked different ahead of time. Maybe schools whose science sucked thought, oh, we need to do something different, and they jumped on board. And then within schools that did decide to jump on board, we have a before and after designation as a time varying predictor. So then you put that in as a dummy code, and that's an intercept shift. Like after the program went into effect, did scores increase? But then if you make that interaction of that switch with time, then you can allow the subsequent change over time to switch as a function of them having this new program or not. So off topic example, but the same problem. Like if everybody didn't do the thing that you're interested in using as the time metric, you can't use it as a time metric, but you can always use it as a moderator. And you can make them fight, right? Like you could ask, well, and not the people fighting, but the moderators, right? Is it aging that's bad for you? Is it getting sick that's bad for you? Is it whatever's happening during terminal decline that's bad for you? Like you can say, what is the net effect of this after controlling for these other processes? I think that's a lot more interesting than just, oh, look, age is bad for you, because it's not. Being sick is bad for you. Wouldn't recommend that. Okay, let me go through my list here of things. Let's see, we're discussing time-varying predictors, time-invariant predictors, and person-level characteristics, but are all predictors either time-varying or time-invariant? Yes, they are. I think where you get into shades of gray is if, so for instance, I had a student doing a project for this class when I taught it at Penn State, and it was time-varying education in adults. They asked each time the study was conducted what the adult's level of education was. In theory, adults go back to school. They can acquire additional degrees and credentials, but that doesn't happen for a lot of folks. So functionally speaking, his time-varying predictor was not time-varying. It had an interclass correlation of 1 pretty much. So they measured at each occasion, but it didn't turn out that they needed to for the vast majority of the sample. Time invariant just means that it was measured once, not that that was a good idea. So I once had someone fight me about this distinction, and I agree. Like if you ask something, my example is like if you're measuring children over time and it's like you ask strategies about parenting and you only ask about that when the first occasion happens. Well, parenting strategies must change over time as the kid you're parenting changes over time. If you didn't measure that, then you can't talk about strategy as this thing that you've captured. You've captured strategy at age 3 or something that's, very narrow and specific, and you probably should have measured it more often. But if you didn't or you couldn't, it's time invariant. Where things get tricky, though, is in clustered longitudinal data. Because you can have cluster variables that are time varying, and you can have people variables that are time varying. Yeah, it gets worse. I don't want to scare you, but I think the question is yes, there are only 2 kinds and 2 level designs. Either it was measured once or it was measured more than once. Let's see. Oh, question about homework 2. Multivariate Wald test for fixed effects. I use Contest MD for that in Elmer. So in example 2, which are, the one with the grumpiness and the glucose, there are pieces of code in using Contest MD to test the joint contribution of multiple slopes at the same time. So I think I asked for that in your homework as well. So I would refer back to that section, and if you have more specific questions, I can certainly answer those. Let's see. There were some questions about alternative covariant structures in GNR. I'm going to review that in the context of showing how those things become implemented in a structural equation model. So in the same way that having to learn Spanish made me learn English better, I think that like learning the same thing from in the SEM perspective will help you learn multi-level better. Same idea. 2 different languages to express the same concepts. And then last one that I saw, I don't know if we talked about enough, but we'll find out. Fixed and random effects related to quadratic time. So if you're generating predicted outcomes and you have a quadratic model, time squared is what goes into that predicted outcome. If you are generating predicted linear slopes, it's 2 times the quadratic instead of squaring it. That's an easy way to remember it. We're not going to have a whole lot of quadratics from this point out, though, I think. It's mostly linear stuff. All right, that's my list. We have, let me put this over here. We can start talking about lecture 4. Would that be fun? Maybe a little bit? As fun as it can be. Fun is a relative phenomenon. Funner than usual. Not as fun as watching TV or Family Guy, but more fun than doom scrolling. How about that? Yeah. So there are a number of sources that people have written to describe the translation of multi-level models into structural equation models and vice versa. Like I can think of 4 or 5 papers off the top of my head, and it seems like every 5 years a new one comes out. What isn't as commonly done, though, yet is taking those 2 and adding to it the newer world of what is known as MSEM, or multi-level structural equation modeling. So that was the chapter that I put on your reading list that I just finished. I had meant to have all the supplemental materials for the chapter done by the time we hit this unit, and that didn't happen. I'm working on them. But for those of you who are going to be using programs other than M Plus in your projects, I wanted to make sure that I had this done. So it will be done within the next couple weeks or so. Oh, and also your homework ones aren't graded yet because I was going to do that yesterday. And that did not happen. I spent the day at the doctor's and then the pharmacy and, all the things. So sorry. Tomorrow is another, we'll try tomorrow. I think he's going back to school tomorrow. He's doing a lot better than he was, so we'll see. But anyway, so why people don't necessarily, what they don't necessarily talk about in these articles is when you would choose each method. So that's the part that I hope to bring to you is, like, these are all different ways of estimating the same kinds of models. Some of the options have features that are useful in some situations, what you might want to do it this way versus that way. So I want to talk a little bit about that so that you have some flexibility. Because what can happen otherwise is, like, I had a student ask me about help for their dissertation, and they had 3 occasions and they wanted to do some kind of longitudinal thing, and they weren't sure whether it should be a multi-level model or a structural equation model. Can you guess what I said?
Yes.
That's what I said. Exactly. I said, yes, it is. And then I tried to explain that it's 6 of one, half a dozen of the other with respect to a lot of things. But then you get into nuances of what's possible because of software. And that's really the distinction. It's not like what's possible theoretically, it's what software options are built into it. And for certain combinations of things, you need to be in the SEM world. The MLM world is just less flexible overall for that. So away we go. We'll see how far we get into this. So most of the analyses that we've seen, actually all of them, I think in last semester and up to this point, are within what I'm going to call a univariate multi-level modeling framework, meaning that there's one column in your data set that's being predicted. And it is a conditional likelihood that's doing it, meaning that you have to have all of the predictors that are in the model to build a predicted outcome. And then we have the variances associated with that outcome at different levels as one of the things that's being estimated. So in that framework, we can only predict one outcome at a time from the perspective of a construct. So like we have multiple outcomes if you have 3 occasions, right? That's 3 outcomes per person. But if they're stacked in a data set, I'm still thinking of it as one thing that's been measured 3 times. If you wanted to measure multiple things each 3 times, then you would need a multivariate version of a model, and that's really where the world of SEM and MSEM come in handy. So we have univariate, what we know so far. You can trick univariate software into doing multivariate models. So in chapter 9, I talk about this. It's limited in what you can do then. Basically, the main limitation is that if you wanted to look at how outcomes relate to each other, you can only do that as correlations. So it's possible, for instance, to have a growth model set up for X and a growth model set up for Y, and you can see how the X and Y intercepts and slopes are correlated at level 2. You can see how the X and Y residuals are correlated at level 1, and that's about it. You can't turn them into directed relationships. You can't examine moderation. You can't have random effects of the within-person relationship, that kind of stuff that you can have. So multivariate models can be estimated, but not very well. I have not had much luck getting Stata to do these, or Elmer, because there's restrictions on what kinds of correlation patterns you can have. So the biggest one, though, is that the models that we've seen so far clearly delineate what is the outcome and what is the predictor. So like we had recall, and we had intercepts and slopes and residuals for that, and we had age carved up into age at baseline and within person age. In the previous example where we had grumpiness and glucose was clearly the outcome. It had a random intercept and a residual. For corresponding partitioning in grumpy mood, we had to do that ourselves. We built person mean grumpiness and within person grumpiness. And that to me is the biggest problem with univariate. It's the asymmetry in how predictors and outcomes are treated. And if you have a time varying predictor that itself changes over time, then multivariate is the only way to go. It doesn't work otherwise. So you need a multivariate model if you want to have one outcome's variance components be used as a predictor of something else. That's another reason. So let's say that you're looking at changes during high school in something, and you want to know that if kids that improved more on something had better outcomes at 25. So like if you picture your model at the end of like the stream of it, you have like one box, like this outcome measured later on, and you want to know if change during an earlier period predicts that outcome later on. Well, you can't do that in MLM. The intercepts and slopes for the random effects are always outcomes. Always. So to do it that way, you'd have to turn it around conceptually and have whatever happened at 25 be a time invariant predictor of those intercepts and slopes, like foreshadowing. That's what I've recommended to people when they couldn't use SEM for whatever reason, but it's conceptually backwards. If you want to have intercepts and slopes predict something else, then it needs to be some kind of multivariate model to do that. To allow cases with missing predictors. So this is another big reason. In multivariate models, you can have predictors that have missing data if you trick it into thinking they're outcomes. The way that you do that is to ask the software to estimate the mean, variance, or covariance of a predictor. That brings it into the likelihood. Essentially, you're estimating an empty model for it. Then you can have missing data on it. So that solves a lot of problems with respect to dropping cases that have missing time-varying predictors and ambiguity as to whether the person mean should be just the cases that were eventually included in the model or all the cases. If those things yield different answers, then that points to some kind of missing data mechanism that you probably shouldn't ignore. That is a whole class in and of itself, though. The short version is that yes, you can have missing data in the world of SEM if you are willing to turn everything that's missing into an outcome, which then invokes distributional assumptions for it. So this is a suboptimal approach if you have categorical predictors that have missingness, for instance, because then you'd have to find a way to tell the software that they're categorical and that they have missingness as an outcome. M+, for instance, will not let you do that. You can't trick it into pretending predictors are outcome if they need some kind of link function. Another reason that you might want a multivariate model is to measure change over time in latent variables. So if you want to sound fancy, like at a job talk or something, you can tell folks that you're learning how to do latent growth curve modeling. That sounds fancier than this, but that's not this. Latent growth curve modeling is modeling observed outcomes using software for latent variables. That's what it is. It means you bought the same model that you could have fit in Elmer in the SEM store instead. That's what latent growth curve models is. But if you have actual latent variables, so a measurement model, for instance, that you're using observed items to indicate some kind of trait, and you want to see if that trait changes over time, that's what this is, what you can use this for. So growth in a latent variable itself needs a multivariate modeling framework to do that. So we'll see an example of that soon. So two options for estimating what I would call truly multivariate, meaning you're not trying to trick univariate software into doing it. MSEM, this kind of drives me nuts. Folks use this word, multi-level structural equation modeling, even for models that don't really have latent variables. Like in example 2, where we had grumpiness predicting glucose, I fit that using M+, and that makes it a multi-level structural equation model, even though there's no latent variables. The connection why people call it that is because random effects are latent variables. So just having the software estimate a random intercept and a residual, technically those are latent, and that's where we can get into the world of SEM as a title for this. So MSEM is essentially what we already know as multi-level modeling, but happening for multiple different outcomes at the same time, so that you can then examine the connections across them at each level. So that uses long format data. Here are some different packages that allow this. So in Lavon, it is the most limited for MSEM. Currently, it does not have any generalized models or random slopes available. Random slopes being available is the biggest limitation for their multi-level SEM package. OpenMX has a lot more options. I don't know how to use it. You have to specify everything in matrices, and I was like, no, I'm just not. Some of the articles on our reading list that came from the Grimm textbook, they have OpenMX examples along with M+. So if you're interested in picking it up, that might be a good place to start. There's a Bayesian package, BRMS. Has anyone played with that here in R? I think it's just like the Bayes version of Elmer, but it comes up in this context as well. Stata, so SEM, that function in Stata is single level structural equation models. There's a GSEM that stands for generalized, and it also has a multi-level component to it. That's what I still need to figure out for the supplemental materials that go with the chapter that's on your reading list. Hope to get that done very soon, as I said. M+ is the most flexible. It's the between within specification is the way that I'm abbreviating this based on what it looks like in the code on long format data. That's what we're going to focus on in this class. And then dynamic SEM is the same damn thing as this with extra stuff added to what you can do with it. So that's not a different thing. It's well within this family. The alternative then is traditional SEM, or what I'm calling single level. And the biggest difference here is that it's using wide format data. So that changes quite a bit about what you can do and what is required to represent unbalanced time. If you have balanced time, everything's fine. If you have unbalanced time, then you need to make sure that the software you're using can understand that and implement the exact time observations within your data. T-scores is what does it in M+. There's something in OpenMX that does it as well, but I do not believe it's implemented in Lavon, and I don't think it's implemented in Stata GSEM, but I gotta check. I'll get back to you on that one once I get more into the documentation for that. Okay. How are we doing so far? Okay enough? All right, so the between and within then, the way that this works in M+, is that you have a within model, and then you have a between model. And it corresponds almost exactly to the model notation that we've been using with hierarchical notation. Like you write your level 1 model with the beta placeholders, and then you define how they're created in level 2 with a fixed effect, potentially a random effect, and any potential interaction terms as well. Parameters are labeled differently depending on whether they're predicted or unpredicted. So this makes it a little bit tricky. So if you have a variable that is unpredicted, meaning it is a predictor conceptually, but you brought it into the likelihood so that it can have missing data, then it's an outcome instead of a predictor. It will have its parameters listed as means and variances in that case because it's unconditional. It's not an intercept, it's not being predicted. Whereas any variable that is actually predicted as an outcome will have its parameters labeled as intercepts and residual variances. Now, their version of residual means left over. So this gets confusing when you see like residual variance on the within model and you're thinking, yes, level 1 variance is residual, I'm good. But then you see residual variance as part of the level 2 model. It isn't, it's just leftover. It means leftover random intercept variance is level 2 residual, or leftover random slope variance is level 2 residual. So that gets a little bit tricky. If you put in level 2 fixed slopes, they will always show up in the between output, but where level 1 fixed slopes show up depends. There's 2 different ways to set up the model, one with the placeholder notation and one without. If you do not use the placeholder notation, you end up with slopes in the within model. If you do use the placeholder notation, they show up in the between model instead. And the latter is necessary if you want to have random slopes or cross-level interactions. So we'll see examples of this getting tricky in terms of what things actually mean and where it shows up as a consequence of model specification. All right, remember this? A happy little random linear growth model. Nothing scary, not like 17 interactions involving age or any of that nonsense. So I've got this color coded in a way that is deliberate, all right? Not just the red and the blue, but purple, which is the amalgam of the two. Yeah, I'm for real. Then I have this like burnt orange thing. that's going to show up as well. Here's my happy little MSEM. These are the kinds of diagrams that you'll see in the M Plus manual and in other places, although I've added a lot more labeling to it to help us figure out what things map. So in terms of the connection to this equation in composite form here, the betas, which I call placeholders or backpacks because they contain fixed and random effects, they're each predicted, those are latent variables in this world. So this circle is beta 0i. This circle is beta 1i. They are predicting observed outcomes in boxes. So I have my level 1 y in one column, so keep in mind this is long format data, and it is being predicted by a residual at level 1 that has mean 0, of course, because that's how they have to be by definition, and what we would call residual variance, and random intercept, whose mean is the fixed intercept, and whose variance is the random intercept variance. So this circle is our random intercept, essentially. It has the fixed part in it because SEM does not make that fixed versus random distinction very readily. But the fixed effects are the latent variable means. The random effect variances are the latent variable variances. Level 1 time is another column in my long format data set. And this can be balanced or unbalanced. It can be whatever it needs to be, the same as in univariate MLM. So I have an arrow going from the time box to the outcome box. So directed arrows in this system of notation are used to convey slopes from, and then which way it's going is the outcome. So beta 1i is actually the slope, and it has this circle on here because that circle is all this stuff. So it's not just one fixed effect, it is a fixed effect that has variance around it. So this allows individual differences and change over time. And there's an implicit 1 on each of these paths here because they're just contributing directly. So for instance, the residual here doesn't have any kind of weight in front of it. That's why it's a 1. And U0 doesn't have any kind of weight in front of it, so that's why this is a 1 as well. And last but not least, not shown in the equation, but estimated as part of the model and estimated as part of this model would be the covariance between the intercept and the linear slope up here. And so that is indicated by a two-headed arrow, meaning that it's not directed, it's just associated. And for whatever reason, the entire world has agreed on these diagramming conventions. Latent variables are always in circles or ovals. Observed variables are always in boxes or rectangles. So this is not that different. It's just a way of representing the model. There are matrix versions of these equations that I could give you instead. I do not find them useful. So I'm not going to. I'm just going to show you the pictures. So there is the legend for that. So this isn't so bad, right? It's a little weird, but not so bad so far. Here's what the M plus code would look like to do this. So we have a within model. This is within M plus, like just the model part here. I'll show you how it works more generally, but since we're about out of time for today, I'll just say for now, when you list a variable by itself in M plus model syntax, you are saying, hey, can you estimate that variance of that variable for me? Thanks. So if you list it on the within level, that's creating level 1 variance. If you list it on the between level, that's creating level 2 intercept variance instead. This thing with the bar is defining beta 1. Beta 1 is the prediction of y from time. That prediction, that relationship, I have given a name. Lin stands for linear, linear slope of time. So then that is now its own level 2 outcome that can have a variance, it can have a covariance as indicated by with here, and when variables are listed in brackets like this, that refers to their means or their intercepts. So these would be the fixed effects of the intercept and the linear time slope. These would be the corresponding random effect variances, and then this is the random effect covariance right here. Ta-da! Now how are we doing? No. It's not so bad. But if you get good at writing these kinds of equations, then it's a lot easier to write this code because it really is like directly analogous. And my coding style when I teach this stuff is to write out everything so that there's no ambiguity as to what's being estimated or not in the model. But a lot of this stuff would actually happen by default. In reality, you'd have to do far less typing if you wanted to. I just don't like doing it that way. All right, so today was a little mixed bag. We got some review, we got some questions answered, we're starting some new stuff. How are we feeling about things so far? Okay. Can you keep telling me if there's stuff that you want to talk about or go back over again? Don't be shy. I'm not going to assume that you have perfect recall of every word that you've ever heard. That's unrealistic. I don't remember what I say. So don't be afraid to be like, I know we talked about this, but can we do it again? Yes, we can always do it again. Any questions before we call it a day? I have a question about the last example, the time varying one. Hit me. You can talk or you can type. Cheers. Say if you're talking, we can't hear you. Why can we not just use occasion as a time varying predictor? You can, however, your time variable needs to have 0 somewhere within it so that your intercept is within the scale of the observed range of time. And you would need to keep track of the exact distance in time between occasions. So every data set that's longitudinal will have some kind of index variable like this is time 1, this is time 2, this is time 3. But if those are not equidistant, putting in that variable and giving it a slope doesn't make sense, because a linear slope means that you have per unit time. And if the change between 1 and 2 is not the same as the change between 2 and 3, then a unit is ambiguous. So we want to think about what time is, make sure it is measured accurately, and make sure that it has a 0 point that's observed. Otherwise, you can have model convergence problems and all kinds of fun stuff. All right, 1:45. Thanks for being here, folks. I'll sit for a minute or two in case anyone wants to ask questions. Hope to see you Thursday in person. I'm hopeful. That's all I'll say. I can't guarantee anything. I'm hopeful. Fair. All right, go ahead and get started on homework if you haven't. Let me know if you need anything. Thanks for being here. Peace out. Bye for now.